All right, let's get these last four problems of section 4.3 done. The first one is simplifying expressions, and it's pretty much just something to get you comfortable with working with e's. Remember, you shouldn't freak out when you see an e. It's pretty much just a number that's about 2.7 or close to 3. So if you multiply 3 times 3, you get 3 squared. If you multiply e times e, you get e squared. It's the same process, the same rules. So when I see simplify an expression with a bunch of e's in it, the first thing I need to do is take a deep breath and realize that the same rules apply. In this problem, I cannot cancel this factor in the numerator, or excuse me, this in the numerator with this denominator. Even though they're identical, this is a term. It's held together by parentheses and then squared. So that would be canceling a term or a part of a term. That's as illegal with e's as it is with anything else. So have a couple different things I can do. Probably what would occur to most folks first is just clear out the parentheses, FOIL this binomial squared and that binomial squared, distribute the -1 and combine like terms. Because this first binomial squared is different looking than anything we've seen before, I'm going to go ahead and write it down twice so I can FOIL it out. And the same thing with that last term. And then I'm not going to FOIL out the denominator because it's already in factored form. It's already something times itself, which is what I'm trying to get the numerator to look like so that I can cancel. I'm going to FOIL here, FOIL there. And when I multiply e to the x times e to the x, I add the exponents. X plus x is 2x. So the outer terms are e to the 2x. I'm sorry, the first terms. The outer terms, when I add the exponent, I get e to the x minus x is 0. Now, I don't just write down e because e means e to the first. I need to say that's e to the 0. And in the next step, I'll say, but anything to the 0 is 1. All right, I'll come back to that. That's the outer terms. Inner terms, when I add the exponents, I get e to the 0 again. Last terms, when I add the exponents, I get e to the -2x. Now, I'm going to FOIL these. And at the same time, I'm going to distribute that -1 just so I don't have to write the whole thing down again. This is e to the x times e to the x is e to the 2x times -1 is -e to the 2x. Outer, I would have e to the 0, but then times -1 is -e to the 0. Inner, I would have the same thing, -e to the 0. And last, I would have e to the -2x times -1 is -e to the 2x. And all of that is still over the same denominator. All right, let's see what like terms we can combine. We have an e to the 2x minus an e to the 2x. We have an e to the -2x minus e to the -2x. And all we have left in the numerator is these 4 -e to the 0s. Again, e to the 0 is 1. So this is -1, this is -1, this is -1, and this is -1. I have -1, -1, -1, -1. Lo and behold, that whole numerator is just -4. -4 over e to the x plus e to the negative x squared. We run into expressions that look like this in calculus all the time, so you have to get comfortable with working with e to the x's or e to the negative x's. All right, all that's left of this section is 3 word problems, 3 applications of the natural exponential function. And when we were talking about E in class today, I don't even think I said the words natural exponential function. I said E is about 2.71828, but I didn't say f of x equals e to the x is the natural exponential function. We called, for example, f of x equals 2 to the x, the base 2 exponential function. This is the base e exponential function. And for reasons we'll get into tomorrow, that's called the natural exponential function. So number 24 is an exponential function w such that w of t, function notation, equals w sub 0, and you'll often see something with a subscript of 0 for an original amount. In the interest formula, we use P for principal, but we could use A sub 0 for original amount. This W sub 0 is the, where does it say it? The original weight of crops such as maize, cotton, and soybeans. So we have the exponential function that will calculate the approximate weight of a crop upon emergence if the original weight is W sub 0 times e to the k times t. This k is called your growth constant. And we have to be given some units on t. This says t is the time in days. W sub 0 is the original weight of a plant, and W of t is the weight after t days. It's often difficult to measure the weight of a plant when it first emerges from the soil. You would have to yank it up to weigh it. So that's not a good idea. If for a species of cotton, the growth constant is 0.21 and the weight after 10 days is 575 milligrams, estimate the original weight. All right, we have an equation with 1, 2, 3, 4 variables in it. If you give me the values of 1, 2, 3 of them, I can solve for the 4th. We have K is 0.21. The weight after 10 days means T is 10. And the weight after 10 days is this much. That's not the original weight, but the weight after 10 days, that's W of 10. So if we put this growth constant into that formula, W of t equals the original weight times e to the 0.21 t, then we have an equation that we can use to solve for any weight if we knew the original weight and the time, or in this case, we can solve for the original weight when the time is 10 days, if we let W of 10 be 575 milligrams. So 575 milligrams is the original weight, which is what we're solving for, times e to the 0.21 times 10 days. Remember, e is not a variable. W sub 0 is the only variable, and to get that by itself, all we have to do is divide both sides by this expression. I'm not going to pick up my calculator until I have that W sub 0 completely by itself. I'm going to get it by itself by dividing both sides to the, I'm going to go ahead and multiply the 0.21 times 10 and just call this e to the 2.1. So W sub 0 is 575 divided by e to the 2.1. And how you punch that on your calculator just depends on what calculator you're using. If you're having any trouble getting the right answer, then let me know what kind of calculator you have, and I'll be happy to help you with it. I've already punched that and gotten 70.41 milligrams was the original weight of this plant after 10 days, the original weight, if after 10 days it weighed 575 milligrams. All right, the second problem is about population. Population of humans and the population of deer or population of bacteria in a Petri dish. All of those are examples of exponential growth. Populations that are getting big very, very quickly until the population runs out of resources, and then the population crashes. It happens with, like I said, deer. It happens with bacteria in a Petri dish, and unfortunately, it will happen with humans. So number 26 says the 1985 population estimate for India was 766 million people. Now, we can just use the 766 without the word million or without adding all the zeros, as long as we remember to put the word million or all those zeros in our answer. I'm just going to say the original population, or the population in 1985, was 766, and keep up with the word million. The initial time is 1985, so let 1985 represent the original time, or t equals 0. If in 1985, if when t equals 0, the population is 766 million, and the population has been growing continuously at a rate of about 1.82% per year. That's a rate, that's our R. If we change the 1.82% to a decimal, we'll have R equals 0.0182. And we're supposed to estimate the population of India in the year 2015. Well, what will T be in 2015 if T equals 0 is the year 1985? 2015 is 30 years after 1985. And so in the year 2015, T will be 30. Now, anytime you're talking about exponential growth and decay, you can use the continuously compound interest formula. This formula that we were given in number 24 really was the same as A equals P times E to the RT. It doesn't matter what variables you use. This is original weight. This is original investment. This K is an interest rate. This R is, this K is a growth rate. This R is an interest rate. This T is time, that T is time. So on number 26, if we just want to use the continuously compounded interest formula for the population in India, we can. And estimate the population of India in the year 2015 means we're looking for A when P is 766 million, R is 0.0182, and T is 30 years after the original time. The amount of people would be 766. I'm just going to keep up with the word million times e to the 0.0182 times 30. And I have that exponent in parentheses to make sure that my calculator does the 0.0182 times 30 before it raises e to that power. Now I'm going to punch that on my calculator and then make sure I put the word million back on my answer. So I have 0.0182 times 30, and I'm using the cursed backwards calculator. So I have to have that exponent on my screen before I hit my E button. And then that times 766 is approximately 1,322.3717. I'll tell you how many decimals to keep up with. But remember that this is not 1,322 people. This is 1,322 million people. So actually to write that without the word million, because, well, this didn't say whether to leave my answer in thousands of millions or to get rid of the word million and put the decimal or put the zeros back on there. Let me write down 2 more decimal places. 3, 1. To write that without the word million, I would need to move the decimal 6 places to the right, because a million has 6 zeros. That's the approximate population of India in the year 2015. If we had plenty of time, since 2015 was 5 years ago, we could actually Google the population of India in 2015 and see how close that is. If the directions here had said round to the near, if the directions had said how many million people will be in India in the year 2015, I could have just left it 1,322 with the word million after it. All right, one last problem. Number 28 says the radioactive isotope Na24, radiosodium isotope, used to locate leaks in industrial pipelines and to study electrolytes within the body, decays continuously. That word continuously is what tells me, regardless of what this is actually about, I can just use the continuously compounded interest formula. Radioactive sodium isotope decays continuously at a rate of 4.62% per hour. That means R is, as a decimal, 0.0462. And my units on time is hours. The big difference in using the continuously compounded interest formula when you're talking about investment, that T has to be in years. But when you're talking about anything else, the time period just has to be specified. So here the time period was per year. Here the time period is per hour. Approximate the percentage remaining of any initial amount after 30 hours. Well, once again, we have an equation with 4 variables in it, but we're only given the value of 2 of them. We're given R and we're given T. We're looking for what percent of the original is left after this 30 hours. How do you get a percent of an original? I'm going to call this P, this original amount, P sub 0 to keep track of it. If you want to know what percent of the original is left after 30 hours, that percent is the new amount as compared to the original. What percent of original is A? If that was the question, you could say P times the original is A. To get that percentage, you just divide both sides by P sub 0. That percent will be the new amount divided by the original amount. And that is e to the r times t, where r is 0.0462 and t is 30. So if I just have e to the 0.0462 times 30, I'm going to punch that on the calculator real quickly. And then raise e to that power. I get darn close to wait, something's bugging me. Oh, I know what. This e to the 0.0462 times 30, that's what A is. That's the amount after 30 years. And then the original amount was just e to the 0.0462 times 0. This is the amount after 30 years. And the amount we started with, that's just, damn it.